So we're going to have a little look at some revision on the first topic in Year 11 Chemistry, which is 1.1 Atomic Structure. So the first little section in this topic is about the structure of the atom. So what you have to know is what the atom looks like, and what the different parts of it are, what the different names of those parts are, and where you find them. So you should recognise this general picture of the atom. So it's got the bit in the middle, and then these shells around the outside. So if we label this wee diagram here, the section in the middle is known as the nucleus, right at the centre of the atom. It's made up of two different particles here. The ones I've labelled with the pluses here, they're known as protons, and the ones beside them which have got no charge are neutrons. So protons and neutrons together make up the nucleus, they're in the centre of the atom. Around the outside you've got some little dots here, they're going around little circles, they orbit the middle, a bit like planets around the sun. Those little dots are known as electrons, they've got negative charges. And they are found in, you can either call these orbits or you might see them more commonly called shells. So that's the general kind of parts of the atom. You need to know a few characteristics about those parts. So you need to know about protons, neutrons, electrons, their relative masses and relative charges. So the mass of these particles is just how heavy they are, and the word relative there just means that we're looking compared to each other. So obviously all these different parts of the atom are very, very light, so we're not going to measure them in grams, that'll be a very small number. All we're interested in is how they're compared to each other. If we look at that, protons and neutrons have got the same mass, so we give them number 1. They're equally as heavy as each other. But electrons are much, much lighter than protons and neutrons. The number we give for it, or the fraction we give for it, is 1 over 1840. What that basically means is if you were counting out electrons, you'd have to count out 1840 electrons to get something with the same mass as 1 neutron or 1 proton. So basically electrons are very light compared to protons and neutrons. Charges, so we're going to have one which is positively charged, one negatively charged, one neutral. You can use the words, the names of these particles kind of guide you. P, I always think of P for positive, so it gets a +1. You do have to remember the 1 because that tells you how big the charge is. Neutron sounds a little bit like neutral, so it's got no charge, so that's a 0. Then electrons have got the opposite charge as a proton, so they get a -1. So the plus and minus means they're oppositely charged, the two ones mean the charge is the same size, so you have to write down both the sign and the number there. One little fact that's important to realise about most atoms, or all atoms in general before they become ions, which we'll look at later, is that they are neutral. So overall, you've got positive charges, negative charges in your protons and electrons. In an atom, you've got the same number of protons and electrons. What that means is that the overall charge cancels out, which means that the atom overall doesn't have a charge, it's neutral overall. So how you'd write it down in a sentence would be, atoms are neutral because the number of protons is the same as the number of electrons, and therefore the charges will cancel out. So first little subsection, structure of the atom, that's what you need to know. So from that structure of the atom, we end up with two very important definitions for this topic, which you need to be really comfortable with. The two definitions are the atomic number and the mass number. What the atomic number is, it's the total number of protons in the nucleus of an atom. And the mass number is the total number of protons and neutrons in the nucleus of the atom. So these are very similar definitions. So obviously in the atomic number you only have protons, but mass number you've got protons plus neutrons. The atomic number is the number that defines what an element is. If you look at your periodic table, the key thing that separates all different elements is they've got different atomic numbers. Well, some cases you can end up with the same mass number. You can never have two elements having the same atomic number, so they all have different numbers of protons. The reason we've got the mass number is that the only two parts of the atom which actually are heavy are the protons and neutrons. So if you want to know how heavy an atom is, they're the only two parts you're really going to be counting up, protons and neutrons. Electrons are so light they don't really count towards that number. So there are a number of ways we can use these two numbers, the atomic number, mass number. The first way we can use them is actually to work out the number of protons, neutrons, electrons in any given element or any given atom. So we'll need to make use of both the atomic number and the mass number to work out protons, neutrons and electrons. So it's easy to see this with an example. So how this would play out in an exam is you'd be given an element. For example, if we look in your periodic table, you might be asked by carbon. And the question would be, work out the number of protons, neutrons, electrons in this atom of carbon. The two key numbers are here, 6 and 12. You need to know what they are. You can't kind of like learn off by heart, but there is a little key down the bottom of your periodic table. It says that the bottom number B is the atomic number, the top number A is the mass number. So 6 must be the atomic number and 12 must be the mass number. So that's the information we've got in the periodic table. Atomic number 6, mass number 12. If we think about our definitions, and if we think about the fact we have to work out what the protons, neutrons, electrons are, the easiest one to work out always is the protons, because the atomic number's definition, it is the number of protons. So in this case, we can work out very quickly that we've got 6 protons in that carbon atom. The next one is probably quite easy to work out is the number of electrons, because if you think back to this fact here, that atoms are neutral because the number of protons is normally the same as the number of electrons. If there's 6 protons, there must therefore be the same number of electrons, so there's also 6. Last one sometimes takes a wee bit more work, number of neutrons, because there isn't like a neutron number. The mass number includes the neutrons, but the number is the protons plus neutrons. So what we basically have to do is subtract the atomic number, protons is just by themselves, away from the mass number to work out how many neutrons are left over. In this case, it's not too hard. You're going to do 6 taken away from 12, which gives you 6 neutrons. So protons just come straight from the atomic number. Electrons also come from the atomic number because they're the same as the protons, and the neutrons come from. The next thing we can do with just the atomic number is we can use it to work out where the electrons go in the atom, which no one's found in the electronic configuration. So in this example, you'd be given an element and be asked to draw a diagram of where the electrons are for that atom. Now there are 2 steps to this. In the first step, you have to work out how many electrons there are, so you're going to need to use the atomic number here, because protons equals electrons. Then we need to remember some rules about where those electrons go. So the rules are, you can get 2 electrons in the first shell, 8 in the second shell, 8 in the third shell. So if we look at the example, if you stick to carbon, we worked out previously that you've got 6 electrons in a carbon atom. So we look at our shell rules and we can get 2 of those electrons in the first shell and up to 8 in the second, so we only need to put 4 in there to get up to 6 electrons. So normally you show these electrons with X's just to make them sort of stand out. In the first shell you kind of put them opposite each other, and then in the second shell and third shell you normally start at 12 o'clock and then you go to 3 o'clock, 6 o'clock, 9 o'clock. Now that is actually carbon all done because it only has 6 electrons. If we had to put more in, we go back and do another lap of this shell to get up to 8, and they all pair up. So that's how we use the atomic number to give us a number of electrons, so we can draw diagrams of where the electrons go in our atoms. We've got another little use for the mass number, which is working out different things about isotopes. Now isotopes have this slightly long definition, which you do have to know off by heart. It's atoms of the same element which have the same atomic number but different mass number. Now what that means is an example, which is probably easier to see. A very common example would be chlorine. There's actually 2 different types or 2 different flavours of chlorine. They both have got the same atomic number, so it means they've got the same number of protons and electrons, but the difference is their mass number is slightly different. You've got one with a mass number of 35 and one with a mass number of 37. If you think about what that means is, we've already said the protons and electrons are the same, because the atomic number is the same. It just means they've got the different number of neutrons. So one's a bit heavier than the other, but apart from that, they're not really that much different in terms of how they behave. But what we do have to do with these 2 mass numbers of these 2 different types is maybe work out an average mass, so we know what to put down in the periodic table. So what that's known as is calculating the relative atomic mass. So what we mean by relative atomic mass is it's a weighted average of the masses of the different isotopes of an element. So basically means we're trying to work out an average mass for these 2 different isotopes here. The reason we got a weighted average is we have to take into account how much of each there is, because it'd be easy to look at these 2 examples of chlorine. Be easy to look at these and think that the average must be 36, because one's 35, one's 37. What we haven't told you so far is that these are not in 50-50 proportion. We've only got 75% of the light one and 25% of the heavy one. So there's a bit more of the light than the heavy. We have to take that into account. The sum we use to work out that average is this. Now this sum does look a little bit complicated, but it's not actually that hard to use. The mass of the first isotope, which in this case could be this one here, which is 35, multiplied by its abundance, which normally is just its percentage, so 35 times 75, plus the second one, which is mass of 37, with its abundance of 25. Now I've only got 2 here. You could have examples where you got more than 2, but you just keep adding on the mass times the abundance plus mass times the abundance for however many you've got. Then you divide that by 100 to get it as a proper average. So in this case, what you do would be the mass of the first one, which is 35, times by 75. Add on the mass of the second one, 37 times by its percentage, 25, divide by 100, and just type that onto your calculator. What you'll come out with is the average mass, taking into account the percentages, which is 35.5. So that's a little summary of everything you need to know for for atomic structure.